All right, it's time for the Fundamental Theorem of Calculus Part 2. This is the workhorse part of the Fundamental Theorem of Calculus. You're going to find this very useful. Here we go. It says, this is the theorem. It says that if f of x is continuous on the interval from a to b, closed interval a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F of x is any antiderivative of little f of x. Now we know from the first part of the fundamental theorem that little f, because it's continuous, does have an antiderivative, so it's got a whole bunch of them. In fact, actually that's going to lead us right into the proof here. That is, we know that g of x equaling the integral from a to x of f of t dt is an antiderivative of little f. So any other antiderivative would just have to be this one plus a constant. Okay? So let's look at capital F of b minus capital F of a. Well, because capital F is going to be just this one plus some constant, and capital F of b is g of b plus c, and then minus f of a, which would be g of a plus c. Right? Just plugging in b for x and then a for x and subtracting. So what happens here is the plus c and the minus c go away, and I've just got g of b minus g of a. Well, let's write that for what it is, right? Because g is this integral. G of b is the integral from a to b of f of t dt minus g of a, which is the integral from a to a of f of t dt. Come on now, what's going on? F of t dt. Well, what's the integral from a to a of f of t dt? That's 0. So I've got the integral from a to b of f of t dt. I actually wanted this to be the integral from a to b of f of x dx, and it really doesn't matter what your variable is at this point, because this is just a number. Yeah. So there you go. The Fundamental Theorem of Calculus Part 2. If you want to find, how's it go? If you want to find the definite integral of a function from a to b, all you got to do is find an antiderivative and plug in the endpoints and subtract. Let's do an example. How about the integral from 0 to 2 of x squared dx. I think we estimated this one earlier. I think we did this one with a Riemann sum. Let's do it this new way. So according to the Fundamental Theorem of Calculus, it says find an antiderivative. So antiderivative of x squared would be x cubed over 3. And I'm going to introduce some notation as we're doing this. The way we usually write this is an evaluate at. Evaluate at or evaluate between 0 and 2. So I'm going to plug the 2 in. That would be 2 cubed over 3 minus plug the 0 in, 0 cubed over 3, for a grand total of 8/3. And I'm pretty sure that's what we got when we did this using Riemann sum, the limit of a Riemann sum. Right? I'm guessing you're feeling that this is substantially easier than using the limit of a Riemann sum. In general, it is. in general, this fundamental theorem of calculus part 2 really makes this calculating of integrals pretty simple. Find an antiderivative, plug in the endpoints and subtract. Right? Another one that that I think we looked at in class. How about the integral from 0 to pi of sine x dx? This is, you know, one bump of the sine curve, and the question is, what's the area under there? Well, find an antiderivative of the sine. Well, the derivative of sine x is cosine x, so the antiderivative would be minus cosine x. Evaluate between 0 and pi. So I've got minus the cosine of pi, minus the cosine of 0, not theta, 0. Cosine of pi, I got to take a quick look at the cosine curve. Oh yes, -1. So I have negative 1 minus the cosine of 0. Cosine of 0 is positive 1. Anyway, I get a grand total of 2. The area underneath one bump of the sine curve. This was, when I first learned this, was kind of remarkable to me. Anyway, the area is exactly 2. So that's the fundamental theorem of calculus part 2. The trick is going to be, can you find antiderivatives? And so we're going to have to spend some time looking at how do you find antiderivatives. I mean, we started talking about it in section 4.9, and now we find, yeah, this is going to not only, you know, help us to do acceleration, velocity, position problems, but this is going to let us do area calculations. But the notion of finding an antiderivative is related to the notion of calculating areas under graphs.